In this problem, we have a diver that is going to jump off of a cliff into some water. And so if I were to make a quick sketch of the cliff, it might look something like this. And then we'll say there's some water here at the bottom. The diver, let's say, is running, and they approach the edge of the cliff, and this is a classic horizontally fired projectile. I'm going to call the initial speed VO. We do know that ultimately their trajectory will be a portion of a parabola. One of the mainstays of the kinematics unit is the idea of a horizontally fired projectile. And we recognize that we have to separate what's happening horizontally from what's happening vertically. If I were to do this formally, I'd say, hey, in the horizontal direction, there is no acceleration. But there is in the vertical direction, which means I'm going to have to use some kinematics formulas. We know that the initial speed in the y direction is equal to 0. Notice that the initial speed in the x direction is not equal to 0. In this case, it's equal to VO. All of this initial speed is horizontal and in the x direction. The acceleration is going to be, let's just use negative 10 meters per second. And the height is given by the height of the cliff. Let's just call it h. We would use a kinematics equation. I think it would make sense to use the first one, which is y final is equal to y initial plus VOYT plus 1/2 AT squared. And we know that the initial y component of velocity is 0. I subtract y naught from both sides, and I get delta y, which is the same thing as height. So let's just call that h. And that's equal to 1/2 AT squared. And if I solve that for time by multiplying both sides by 2, I get 2 times h is equal to AT squared. And then I'm going to solve it for t by dividing both sides by h and taking the square root of both sides. I get 2h divided by a is equal to t. So notice that the only thing that affects the amount of time that the diver is in the air is h. It doesn't matter how fast he or she is going left to right. So when the person is running twice as fast, they don't stay in the air any longer. That's one of the common misconceptions for first-year physics students. So if I go back over to the left-hand side and we recognize that the person is not accelerated, we can say that the horizontal velocity is just going to be equal to the horizontal displacement delta x over time. How far you go side to side divided by the time that you're in the air. So notice that the time is not changing in either case. So I could say that the initial x component of velocity is proportional to, I'm going to use this little fish symbol. I'm not trying to be fancy, but this in mathematics means, hey, it's related to, I'm switching the equal sign to a proportional sign because I left the t out of the denominator, because the t isn't changing from one instance to the next instance. So now I can just say that the initial x component of velocity is proportional to delta x, directly proportional. So if we run twice as fast, we land twice as far, and the correct answer in this case is letter C.